Hello, my name is Ruby Chakraborty, and here is my Lab 1 video. Alright, as an introduction, this experiment uses statically charged tape to observe charge interactions between different objects, like neutral objects, like a book or a notebook, my hand, different charged objects, like a charged pen, and between other pieces of charged tape. My initial expectation was that if I brought two tapes together, they would repel each other because they have the same force. And as you'll now see, this ended up being correct. All right, let's go on to the interactions.
So over here we have my U-tape that is on my kitchen ledge. It's not moving or anything, it's pretty still, but when I put my hand near it, it's instantly attracted to my hands. Wow! Here's how the U-tape interacts with a neutral object. It's a less strong attractive force than it was with the other U-tape, but it's an attractive force nonetheless. I have two U-tapes. As you see, they really don't like being with each other. They don't even want to come near each other, actually. Both of these U-tapes, they have similar charges. The same charges, actually. That's why they're repelling each other, instead of sticking together.
So with all of that in mind, now we can experiment with a negatively charged plastic pen. So if the U-tape is positively charged, it would be attracted to the plastic pen because opposite charges attract. If U-tape is negatively charged, then the U-tape would be repelled by the plastic pen because like charges repel. And if it is neutral, then the tape would be weakly attracted to the pen due to polarization. So let's see what happens.
Okay, so here I have another U-tape and a charged plastic pen. When I bring this pen near the tape is attracted to the pen, so that means that they have opposite charges.
So since the U-tape is attracted to the pen has a negative charge, this means that the U-tape has a positive charge. So let's go on to the next part of the experiment. Before this experiment, we had to answer a number of questions, like since the momentum of tape B is not changing, the net y component will then equal to 0. So knowing this, we could then make a free body diagram that shows the two different forces that are acting on the tape. One is the electric force, which is F equals to EQ, and the other is the gravitational force, F equals to mg. Because there is no momentum, right? The electric force and the gravitational force will equal to each other. And in order to determine the gravitational force, we have to measure the mass of the tape. We know that the mass of the tape is 1 gram per every centimeter. And my tape is 20 centimeters long, so the total mass of the tape would be 0.0002 kilograms. So let's see what happens in the experiment.
And over here we have the two positively charged U-tapes that are interacting with each other. Without the tape at the bottom, it falls flat. But over here, this force acting on it creates a distance in between the two tapes. That's all.
Alright, that's really cool, but now we have to do some calculations. So determining the magnitude of the gravitational force on the tape, we find that F equals to mg, which ends up equaling 0.00196 newtons. From there, we then carefully measured the separation distance between the two tapes, which ended up being 2.6 centimeters. Using these two numbers, we can then relate the the F equals to G equation with the E times Q equation to get this equation right over here in the middle. And then after that, when we plug in all the constants and everything like that, we end up getting that the charge on tape B equals to 1.47 times 10 to the power negative 16. Using the charge on the tape, we can now calculate the corresponding number of electrons that are in excess or deficiency on tape B. There will be a deficiency of electrons on tape B, mainly because it is positively charged. So we can calculate the number of electrons by calculating the number of atoms in the tape that, it's supposed to be. So we see that we can calculate the volume, and we know that the material is a low-density polyethylene, which has a certain type of density. And using that, we can calculate the number of atoms using this equation that says the number of atoms equals to Avogadro's constant times density times volume over molecular weight. So using this formula, we can calculate the number of low-density polyethylene molecules, and from there we can calculate the number of hydrogen atoms and carbon atoms, and from there we can calculate the theoretical number of electrons there are supposed to be in the tape. And with this theoretical number of electrons, we can also calculate the total theoretical charge that's supposed to be found on this tape. But when I tried to do the same thing with the total measured charge, it seemed to be very off, so I will have to revise those calculations. Now we can go on to the coding section. So the coding section is basically a rehash of all the calculations that we did before. First, I coded the tape as two different boxes. Those tapes are represented by 2-point charges, P1 and P2. We can then calculate the force equation, which is F equals to mg. And then after that, we can calculate R, our magnitude, our hat, and using these values, we can then use to try to find the charge, the same way that we found it in the last slide. And from there, we can now calculate the electric field, and we can then represent these forces using arrows. So here's what it ends up looking like. Here's another written out, more clear version of the equations that I used and the different procedures that I used. So you can pause this video to check that out. But anywho, the most important thing is that the two tapes, they ended up having the same amount of charge. And lastly, as a reflection question, we end up seeing that there's 1.867 times 10 to the power minus 6 coulombs interacting for each tape. The different assumptions that we made throughout this lab included that the gravitational acceleration is 9.8 meters per second squared. There's no air resistance. There's equal masses for each tape. Also, if the charges for electrons and protons switched, none of the observations would change. Like charges, they would still repel each other. If the charges were opposite, they would still be attracted to one another. And lastly, it is important now to handle the charged tapes as little as possible because the charges on the tape would start rubbing off against my skin, and instead of the tape being fully charged, it'll start behaving like a neutral object. Okay, that's all from me. Thank you.